So this is a second lecture by Mr. Dembo. Today he will talk about extremal cuts from sparse random graphs with spin graphs. So I'll send this, how to say, yeah, let me say in Japanese. 単位が必要じゃない人も、学生の人は名前を書くようにしてください。Yeah, please.
Okay, so it's a pleasure to continue with the second lecture. And this lecture will be almost independent of the first lecture, of the overview. So I will, if you remember from the first lecture, we were talking about, I mentioned that the motivation is to deal with complex satisfaction problems and to use a method of statistical physics in order to analyze their asymptotics. And we talked about a few of them. I gave a few examples, and today we will focus on one particular example, that of extreme cuts, that it will serve as a demonstration how we connect constraint satisfaction problems where the emphasis is that we are working on sparse random graphs. The random graphs are measuring average complexity of the problem, and the sparse is because that is a case where the number of constraints per degree of freedom is constant, and that is where the interesting action happens. And the goal is to connect this to a more developed theory of spin glasses, which has been developed in the last 10 years. So the outline of the talk, there will be 6 parts, 5 of them related, and the 6th is not, is really a preparation for the next lecture. So I will start with repeating the problem of the extremal cuts. Specifically, it's a specific constraint satisfaction problem. And then we will move to, as we did in the general review last time, we will go to deal with average case complexity of this problem by using sparse random graphs and look at what is the literature that was done in combinatorics and computer science on this problem before. Then the connection with statistical physics will become through the introduction or the connection between extremal cut and easing measures, specifically antiferromagnetic easing. Then part 4 will be the mathematical result, how to connect the easing problem on a sparse graph with a spin glass model on a complete graph. That's where I will go over the proof of the theorem that I mentioned to you at the end of last time, and I will repeat it again. Then there will be a break. And after the break, we will go over a different problem or a different paper which is dealing with algorithmic issues. This is a companion paper that was written by my co-authors, not with me. And it's the only time in this lectures series that I will also discuss algorithms, but it will be mathematical analysis. So you can see that the mathematical analysis not only give you information of the kind of theoretical information, values and so on, but it can also have somewhat applied application in finding good algorithms. And the last part I will talk about, this will be a Blackboard part, which is about half an hour, where I will do a very quick derivation of analysis by large deviation of the Curie-Weiss model, showing you the coexistence of phases, which I already indicated in the easing model when I mentioned the review on the easing model in Z2. But I will do it instead of Z2 on a complete graph, which is much simpler. So that will be a toy problem to motivate what we will do for sparse graphs on the third lecture. Okay, so the first topic, we are going back to constraint satisfaction problem, and specifically to the extremal cuts. As I mentioned, the first lecture I reviewed few of them. Let's repeat the only one that is relevant for us today. We take a graph, G, finite graph with certain vertices and certain edges, and then we define the notion of a cut on the graph. This is exactly the same slide that appeared in the first lecture. So we have the vertices which are marked by blue circles, and we have the cut, which is this red dashed line. And we can think of the cut as assigning to one part of the graph the value 1, labeling the value 1 those vertices on the left side. And the vertices on the right side I will label by -1. So the cut defines a subset of the graph S, and the cut width, or the value of the cut, is the number of edges which are crossed by the cut. In this particular instance, it is exactly 2, right? Because we cross edges. More generally, the cut size is given by the number of edges with one end in one set and the other end in the other set. And as I mentioned, there is a very easy algebraic relation. If we put sigma I to be +1 on S and -1 on the complement of S, then whenever we have an edge that goes across, the value of sigma I times sigma j will be -1 because there will be an opposite sign. In contrast, the edges which are inside here will get the value +1. So if we look at minus the sigma I sigma j, that is give +1 to the crossed edges and -1 to the ones which are inside, that's exactly the same as taking 2 for every edge in the cut and subtracting the total number of edges. So the total number of edges is a deterministic quantity. It's a quantity depending only on the graph. So up to this constant, we see that the cut size up to a factor 2 is exactly the energy that we put in the antiferromagnetic easing on G. So the antiferromagnetic easing, I remind you, this will appear later in later slides. Antiferromagnetic easing is a probability measure, mu on sigma -1 to the 1 to the v, which is normalized minus beta hg of sigma, and hg of sigma is what appeared in this slide. This what appeared in this slide. Okay. So let's look at some particular cuts that we can be interested in. Okay, so we are not really interested in the typical random cut, but we are interested, as mentioned, in extremal cuts. So there will be 3 extremal cuts that will be of interest to us: the minimum bisection, the maximum bisection, and the maximum cut. The minimum bisection tries to minimize the number of edges that go across the cut. So we are trying to put all our edges, if possible, in the 2 groups and as few as possible between them. So we are minimizing the size of the cut, but when we minimize the size of the cut, we ask for the sets to be completely, perfectly balanced. Because if we don't make this assumption, there is a trivial solution to put all the vertices in one side, no vertex in the other side, then obviously we will not have any edges. So we forgo this by asking for a bisection or a balanced cut. We can also do the complement, that is ask for a maximum bisection. Now we are trying to put the contrary. So to putting all the edges, try to put as many edges as possible in the 2 groups. We are trying to put as many edges as possible in the cut. And the maximum, there is no trivial solution, so we can also look at the max cut, which is the most famous problem, where we just look at the maximum over all the cuts. Here, taking one set, which is everything, and the other side, which is nothing, is not going to help us, because we are trying to put all the vertices on the cut, and naturally, it should be approximately balanced. That's going to give us the error. So we are interested in any one of these 3 problems: mean bisection, max bisection, and max cut. They are all about extremal or optimization over graphs, and we will be interested in finite graphs, but which are large. And the complexity theory question is how difficult it is as the graph size becomes large to calculate the values of these things and maybe find the maximizer or minimizer cut. That will be the computer science type questions of interest here.
The example you want to minimize the cut. In that case, is it still antiferromagnetic?
Sorry?
In the first case, you want to minimize the number of cuts.
Right.
With some constraint. Is it still antiferromagnetic?
No. So the good comment. This problem will actually be ferromagnetic because you change the sign. So one of them, this is a ferromagnetic easing balanced, antiferromagnetic easing balanced, antiferromagnetic easing not balanced, and indeed ferromagnetic Ising knot balance is clear what to do. You just put all of them 1 or all of them -1, which is exactly what I mentioned in the context of the combinatorics problem. Okay. Okay, so the complexity of these problems in a worst case, these problems are known to be hard to solve. Okay, so what does it mean that they are known to be hard to solve? They are what is called NP-hard. I mentioned in the first lecture the notion of NP-complete, which correspond to decision problem, and the notion of these are NP-hard, which is containing that. And in particular, not only is it hard to decide whether the number is bigger or smaller, it's also hard to approximate this number. So even if you don't want the exact number, if I give you a large graph and the minimum bisection is growing with the size of the graph, I don't really ask you whether it's 1,000,001 or 1,000,002. No, I just ask you to be correct within an arbitrary relative fraction of error, right? So I want you just to get to within, determine the number up to plus or minus delta fraction of error. That is going to be hard. This is known to be hard to approximate within 1 plus little order of 1 factor. That is, you want to get an algorithm that will run in a polynomial in the size of the graph time and will produce the answer up to 0.001 error. That's very difficult. Actually, there is an algorithm with semi-definite program. There is a very famous algorithm due to Gomez and Williamson in 95 that gives 0.878. So you can actually get up to 0.878 of the answer in a polynomial time that is fast on any graph that you want. But there is also a proof that came 5 years later by Trevisan's, these people, Sorokin et al., which prove that you cannot do anywhere better than 0.941. Okay? So whatever the optimal constant you can do, on worst case, it is not 1. And actually, under the unique game conjecture or postulate, they proved afterwards that this is optimal. So if you can prove the unique, this is a very well-known problem in computer science. I will not get to it in complexity theory. So they believe that the 0.878, as I said, is optimal. So the problem is kind of solved in this sense, but it's not solved satisfactorily.
Is there any meaning of this number?
This is 16. One of them is 16 over 17, actually. They are not the beginning of some, yeah, and they do not involve pi or anything like that. And I don't know where they come from because I did not read the proof of these papers. So I admit on that. But they have nothing random, no probability. This is it's sophisticated mathematics of the type that is done in theoretical computer science, but it's all worst case analysis of all possible outcomes. We will get to semi-definite programming. We will actually study semi-definite programming in the context of random graphs. So I will explain at part 5, I will explain what semi-definite program is, so you will know what this algorithm is doing. And I will also show you very quickly that it's extremely easy to do it within a factor 2. So up to get to a half, every child can do. But beyond that, no one can do, and to get here was pretty impressive work. So, you know, there is moving the constant up is not a trivial issue. Okay, so now that we have cleared the issue of worst case complexity, we realize this is a difficult problem, like I promised early on. We want to look at typical complexity. That is average graph. And we mentioned what are our average graphs. Our average graphs are going to come from 2 varieties. Either they are Erdos-Renyi graphs, random graphs, or they are random regular graphs. Now, in principle, you can take your favorite collection of graphs, which is more general, and study it. The answer may depend on the graph, in principle, and some of them will be easier to analyze than others. We are just choosing one of these 2, first of all, because those are the most classically chosen as graphs that are studying as a benchmark in computer science and discrete mathematics. And there is a reason for that, because those are also the easiest to analyze. In the Erdos-Renyi graph, what you are doing, you take n vertices, and you, originally the way I described is the Erdos-Renyi random graph. You have number of edges given, number of vertices given, number of edges given, and then you choose a graph uniformly among them. This is a very nice combinatorial way to put it. You assume just number of edges, don't want to assume anything else. The better way to deal with Erdos-Renyi graph is to utilize that this graph is extremely close to a graph where the edges are independently present, each one with a probability p. Just make sure that n choose 2 times p, which is the typical number you will get with match m. So that's how you choose p, or you choose m. And the reason is that what you are getting here is a binomial, and the binomial is extremely well concentrated around its mean, and you can prove that these graphs are in principle, they satisfy the properties that anything that holds with probability 1 on one will hold probability 1 on the other. So that's called contiguous graph models. So if you prove some sequence of such graphs, some property holds almost surely, or with high probability, then you got it for the other one. And we all know that probabilists love to have independence. Okay, this is probabilists love to have independence. This is a good statement. Okay, so there is a parameter here, which is average degree, which you can get by multiplying n by p. And sparse graph correspond to average degree, which is order of 1, or if you go back to this parameter p, it's gamma over n, to make sure that when you multiply it by n squared, it is going to be linear, or the number of edges m grow linearly with n. This is what I call sparse graphs. And the reason for that, because then the number of edges is going to be proportional to the number of vertices, and that's where the game is going to happen. The random regular graph forgoes the independence, because now it requires a fixed degree gamma for every edge. There is also a restriction, of course, that here gamma has to be an integer, whereas here gamma can be a real number, any number from 0 to infinity. It can be non-integer. So the regular graph loses in the independence, so it's harder to analyze whenever independence is being used. It is not contiguous to the Erdos-Renyi graph, because here the degrees fluctuate, and here they are not, and you can recognize it very easily by looking at the graph. However, you gain here that every location around every vertex looks the same. So it's like this is independent, and this is closer to identical distribution, or it's really closest to vertex transitivity. So you can trade them. So sometimes you use that, sometimes you use that. Okay, so there is a long history to the study of extremal cuts in random graphs. I did not invent this problem on the average case. And it starts with a paper of Bldg in 1988, which I will actually go over this paper in principle. And the history of this problem, in general, people try to do what? To take a large graph, random, look at the problem of extremal cut, and try to estimate for this graph ensemble, either Erdos-Renyi or regular. Most of the work was on one of these two, or actually all the work I mentioned here will be one of these two, either regular or Erdos-Renyi, and trying to check how does a mean bisection or max bisection or max cut grow as a function of n. And you see here which is a graph ensemble, regular, Erdos-Renyi, regular. I don't remember what this is. This is probably, I can actually know what this is. This is also Erdos-Renyi, and this is Erdos-Renyi. Mean bisection, max cut, max bisection, max cut, right? Different problems. And what are people doing? There are two types of bounds you can do. They are called concentration bounds and algorithmic bounds. For example, suppose you want to look at mean bisection. Concentration bound will tell you what cannot be done. You would look at the value of a typical cut, and you will prove that all the cuts are sufficiently concentrated that even the maximum is not going to deviate from it too much. So for mean bisection, concentration bound will give you a lower bound. It will say what you cannot do. But if you want to get the number, you need to find an algorithm. That's exactly where an algorithmic bound will come handy. You will find an algorithm, you will analyze what something is doing, and prove that you can do at least a certain amount. Hopefully, if you got your two bounds to combine, then you got the number. Right? So you're playing the game from both ends. One is saying what you cannot do, one is saying what you can do. These problems are dealing with large value of gamma. There is a difference there is a difference, not subtle, there is a qualitative difference between Erdos-Renyi and regular graphs in this business, and is as follows. In a regular graph, the degree is always constant, integer, and you are not going to take degree 1. You're starting with degree 2 or 3, and then the graph will be well connected. In an Erdos-Renyi, as you play with a degree, the graph can shatter. And when the graph shatters, it's easier or difficult to get the extremal cuts. So in particular, there is a phase transition in max cut for gamma equal to 1/2. That's half of the time before you get even the giant component, for those who know. And the difference is that in max cut, you try to put all your edges into the cut. Up to 1/2, you actually can put almost all of your edges into the cut. That is, a number of edges which are not in the cut is actually going to be little order of n. But once you cross the 1/2, some edges must be lost. So there is a phase transition here in terms of the computer science. And then you can study the scaling window, which means that you look again at small gamma around 1/2. And all the other papers have been dealing with large gamma, because large gamma seem to be more amenable to analysis. And that's also what we will do in this talk. And in particular, the paper of Gamarnik et al. So you have Bolovash, Alon, and all sorts of other people starting. This is also only a partial list. And the paper of Gamarnik et al. Actually does use, it's the first paper that does relate to spin glass theory, and uses spin glass theory to repeat the concentration bound, goes back to the beginning, but uses intuition from spin glass in order to improve the concentration, because they know that certain things don't need to be looked at. And what we are doing, we are taking the spin glass relation even one step further, as you will see in a minute. Okay, so what is a typical result that you will expect to get? Suppose we take the Erdos-Renyi graph, but you can do the same with a regular graph, and suppose that gamma is large enough, so we are not looking at 1/2. Then what will happen, for example, to the max bisection? It will be concentrated around, and there is an integer number, there is a product of n and gamma. This is just the number of edges in the graph is n gamma over 2. Right? You have n gamma is the total sum of the degrees. Every edge participates in 2 vertices, so number of edges is n gamma over 2 on the average. So what is this representing? This is just half the number of edges. Half the number of edges is what, as I will show you in a minute, is what you get in a random cut. So this factor simply tells you that you are around the value for a random cut. And what is interesting, if you do it from computer science point of view, is not this factor, but how much can you get beyond it. So in the max cut, the max bisection, you can get bigger than that, right? By some number. This number will still be linear in n, but now only square root of gamma. You cannot utilize, you cannot change the, you cannot take more than half the number of edges. You cannot take 2/3 of the number of edges into your cut. The graph is random. You cannot just collect so many, but you can make a sizable improvement. So this literature that I mentioned was kind of focused on these two numbers, C1 and C2, and kind of slowly, one person got a C1, another person got a C2, then another person got a C1, which is slightly bigger, and another person got a C2, which is slightly smaller, with the hope that eventually we'll get to the right number. So the goal here is to determine a constant that will be the same for both of them and figure out what it is and why it is there. That will be a goal. So I will explain to you now a classical argument, the first argument of Bolovash, which is really a very easy probabilistic argument. It's an application of the probabilistic method, if you want, which actually does a concentration bound. It's going to be sufficiently simple that I can put it all on the board up to here, and it will not involve too fancy stuff. Okay, so we will take, for that purpose, we will take, let's take the graph V has n edges, has n vertices, a graph, and it has n gamma over 2 edges. So I took here the Erdos-Renyi version, but I took the Erdos-Renyi version where the number of edges is determined. But I can take it also the independent one. Now I fix a candidate for the max bisection. My goal is to get the upper bound on the max bisection or the lower bound on the max cut, the on the mean bisection, so the concentration bound. Okay, so I take a particular candidate cut, which is going to be a bisection. So I choose half of the vertices deterministically and see what happens. So let's see what happens. Now, because I'm doing Erdos-Renyi and every edge is put there randomly, I can put all my cut decision in the beginning and choose a graph afterwards. Why not? So if I choose the graph afterwards, half of the edges of the graph are going to fall into my cut, and half of the edges are not, because my cut exactly has a potential of collecting the sets where exactly 1/2 is not exactly 1/2 because there is small changes because you don't allow special. You know, there is, it's n choose 2, and you split them between the ones inside and the one outside, but it's tiny compared to n. So, since each edge is cut with probability 1/2, is put in the cut probability 1/2, on the average, this particular cut will have a width which is a number of edges over 2, or n gamma over 4. And this, as I mentioned to you, is also an algorithm to get 1/2 of the approximation of the max cut, because the maximum value of max cut is a number of E, right? And I can do half of it as follows. I just take few cuts deterministically, 1, 2, 3, 4, and I take the largest one I come up with. With high probability, I will cross the mean at some point, right? So if I take 100 of them, probably all 100 independent realizations are going to be below the mean, is like 2 to the minus 100. So I can get a very good approximation, but only to factor 1/2. This is what I meant, that a general, any cut can do half of the best cut, or any reasonable cut. Okay, but now we try to improve upon it, and the idea is to simply control the tail of the deviation from the mean. So we look at the value of the cut. This is a random variable. S is deterministic. It's a random variable because the graph is random. The randomness here comes from the choice of the graph. The cut is determined. I subtract the mean, and I look at the tail, and I hope to get exponential tail. And I will get exponential tail by using the Azuma-Hofding argument for a martingale difference of bounded increments. I can do that because whenever I choose an edge, the edges are chosen independently. Whenever I choose an edge, the size of the cut is maximally changed by 1, right? Because either the edge fall on there or not. And I can do it and check, and I will get this bound. Actually, in the case of Erdos-Renyi, I can do much better than that because I actually have simply a binomial distribution. All the edges are chosen at random. Half of them, I have n choose approximately n square over 4 edges which are in my cut. This is n over 2 for S times n over 2. Each edge comes gamma over n. So I have a tail of the binomial. I can do the tail of the binomial. This is just the mean. So I'm just doing the tail of binomial. It's like tail of Poisson. I can calculate the parameter, and I will get this exponential Gaussian, sub-Gaussian tail. So I'm cheating here a little bit because Bldg was much more energetic than me. He did it for the regular graph, where you cannot do this argument, and he did it with combinatorics, but nowadays you could have done it for the regular graph with more probabilistic means. For the Erdos-Renyi graph, he wouldn't even bother, because it's so easy. Anyway, what you get out of it is now a bound on the max cut, because you have a bound on each cut. There are at most 2 to the n different cuts, right? What is a cut? It's a choice for n variables, whether they are 1 or minus 1. So there are 2 to the n different cuts. This is going to cost you a huge amount, but if you choose your delta here to be small delta times n times square root of gamma, you will cancel, the delta square will cancel this guy, and will leave you an extra n and a delta square. So if you play with this constant delta until you beat the 2, you get something that goes to 0. And this way you can get yourself a constant C here. It will not be optimal, probably. It will not be elegant, but it will be something. So that's a concentration bound. And that's a basic one side of the argument. You can see that this is not going to, it's too naive to give you the right answer, probably. But you might try to now tighten sharpen the screws until you get it to work. Okay, so the conclusion of this is that the max bisection is n gamma over 2 plus some constant n over 4. Mean bisection is n gamma over 4 minus another constant. Now, this is not very good because you need still a lower bound, non-trivial lower bound on this, and non-trivial upper bound on intersections. Those come from the algorithmic bounds, and those are much more tricky to do because they involve doing something, not just applying a probability in a relatively straightforward manner. The moral of the story is that the n gamma over 4 is trivial and not what you care about. What you really care about is the next term. So our goal is to get the next term. Okay, to get the next term, we are going to switch gears and get statistical physics to help us. So far, there was no statistical physics. We started with computer science. We moved to probability by using random graph. Now we are going to introduce statistical physics. The same pattern that I did in the first lecture, in general, now we are doing it on this particular example. And we already did it a little bit before in the introduction lecture, but I will do it now slowly. So we take our Ising Hamiltonian for our graph. Okay, so what is the Ising Hamiltonian for the graph? It is going to be the sum of sigma I, sigma j over ij in E, and the sigmas are going to take the values -1 and +1 to the power n, because I'm assuming that my graph always now have n vertices. I'm looking at graph with n vertices. I will have Gn, which is Vn, Pn, and Vn is n. N means that the labels, the vertices are labeled 1 to n. And I'm assuming that Gn is either belonging to G regular n gamma or Gn belonging to Gn gamma over n, and gamma is fixed, and n goes to infinity. That is my goal. And I'm going to remove these minuses around here because I'm anyway, as mentioned by Ryoki already before, I'm anyway going to choose sometimes beta positive and sometimes beta negative. So let me cancel both minuses because I'm anyway not going to do real physics. So I just cancel all the minuses. Now, one more thing, I would like to normalize this quantity because if I choose different gammas, I get a different number of edges here. Right? So I get a different number of edges here. Let me put an n to everybody. So what I'm going to do, I'm going to normalize, this is just a normalization constant by 1 over square root of gamma to put them in the same, on the same level. Now, this is really, you could have embedded it into the beta, right? I'm essentially choosing a scaling of beta as I change the graph parameters. Okay, so that's what I have here. Now let's look at the max cut problem. Well, that's the simplest problem. The max cut problem is an unconstrained problem. I don't need to constrain. So I have the sigmas are S correspond to, the cut correspond to things which are +1. The size of the number of edges, En, is n gamma over 2. The size of En is chosen to be n gamma over 2. You know, you just make sure that n gamma over 2 is an integer or round it up. And let's see if I do this operation 1 minus sigma I, sigma j over 2. If I look at this operation, what do I get? If the cut connects -1 to 1, then I get a -1 here, +1. This will be 1 over 2 over 2, 1. So an edge which has sigmas which are opposite will give me a 1. An edge which has sigmas which are the same will give me 0. If I sum, I just get the cut. If I choose a maximum over S sigma, that's the same as a maximum over S. That's really the max cut. So I just wrote the max cut in terms of variable sigma, which are plus or minus 1, like here. Okay, now let me work it out. This 1/2 can go out. It's 1/2 E, right? I just sum over E. And what I get from the rest of it, I get -1/2. I change the max to the mean due to the sign change, and write the sum of sigma I, sigma j. Or I can rearrange it in terms of my Hamiltonian here. Right? I divide by square root of gamma, multiply by square root of gamma. It's just a strange looking algebra like this. Now remember that my answer is supposed to be, for the max cut, is supposed to be n gamma over 4 plus square root of gamma times something. So this something is just going to be this minimum. Right? So I try to make the minimum as negative as possible, and this will give me the number I'm after. So that's why I scale by square root of gamma, so I see exactly what I need to find. In a very similar manner, if I want to look at the bisection problem, I need to restrict attention to S, which is n over 2. What does S equal n over 2 means? It means I should have exactly the same number of pluses as minuses, which is the same as saying that the total sum should be 0. Okay, so I'm looking at omega n. This is called balanced configurations. Omega n is all the sigmas such that sum sigma I equal to 0, and this corresponding to S bisection, or the size of S is n over 2. So the bisection problems involve the same story, max bisection, min bisection, just changing from min to max, and working over balanced configuration instead over non-balanced configurations. Now we related our three problems into questions about ground state energies of easing, that is minimizing or maximizing various Hamiltonians. This was just this was just algebra, and it was really high school algebra, or even less than high school algebra, because I don't think I did anything except multiplying and adding. Okay, so if I come back to this slide, to what is written here, I take my easing measure, as I mentioned to you, with a normalizing constant. Now I can write the n, because somehow the notion of what is a Gn is kind of known from the beginning. So I have a measure over plus minus 1 configurations, and let me restrict it for sigma, which is an omega n, to deal with the mean and max bisection. So I restrict to balanced configuration. I calculate the free energy, the partition function, sorry. The partition function is a normalizing constant, now taking only over balanced configuration, because those are the only configurations I care about. It is going to be ferromagnetic if beta is positive, antiferromagnetic if beta is negative. That's the notion we have. And we are taking the limit, if we take the limit 1 over beta log of the partition function, what I call the ground state energy, it will have the effect of taking here a log, dividing by beta, and sending beta to infinity. That will enhance either the largest or the smallest, depending on the sign of beta. So I get either the maximum or the minimum, meaning that the answer to mean bisection and max bisection is done by calculating the ground state energy for antiferromagnetic, ferromagnetic, and antiferromagnetic easing models, and then taking the large graph. Okay? So that's what I want to do. So I connected the problem to a problem in physics. Okay, so what are some insights that one can get from statistical physics? So I will start with some conjectures, that is, some statements which you can get from statistical physics maybe, but I will actually start with one conjecture, which is kind of very interesting. There have been many other conjectures before, starting with a paper of Fu and Anderson from 1986. In the book of Mézard and Parisi from 2001, there are lots of conjectures and predictions and stuff like that. But I will talk about one particular conjecture, which is relatively recent, of Debrova and Bocher, two statistical physicists from 2010, 6 years ago. They checked and found, numerically really, not even without a justification, without a theoretical physics justification, they simply ran many numerical simulations. They look at the value of max bisection, mean bisection, and max cut for graphs which are regular with gamma fixed and n large, and they found that with high probability, you have this great symmetry. The minimum bisection and maximum bisection, they are both centered around En over 2. And one of them deviate to one side, because maximum, so you get bigger. The other one deviate to the other side. They found out that the deviations balance each other out in the sense that each of these deviations we already know is of order n. But the difference between them is actually of order little order of n. So somehow you have some inherent symmetry here. Now, you can say, they are really minus of each other, but not exactly minus of each other, because the edges are really 0 and 1. They are not, you can just check. It's not true that these variables are symmetrically distributed, a priori. But in reality, they happen somehow asymptotic into mismatch. And this was the motivation of our work. We wanted to do something in this direction. Nobody knows how to prove this conjecture. And essentially, it's just numerical simulation that shows very convincingly that it's true. But we have no idea how to do it for fixed gamma. And what our work will be is to justify it for a very large gamma. And in the process also calculate the C that was given, that was after people in computer science were after. Before we do that, let me mention one result that was already using statistical physics. This is a result, mathematical result using statistical physics ideas. You take both of these ensembles, and you calculate the limit value of the max cut of the. You can do it also for the bisection, I guess, but Bayati, Gamarnik, and Tetali 7 years ago studied the most well-known problem max cut without a constraint, and they proved that there is a limit, right? They proved that 1 over n, the value converges. However, they did not gain any information about the value of this limit because the method in which they used is subadditivity. They related a graph of size n to a graph of size m plus n. And they used it to argue, first of all, you can easily prove that these variables, when you divide by n, are concentrated around their mean. So you can replace the question about convergence of variables with convergence of expectation. This is not very difficult. It's like all of us concentration argument. So now you have a sequence of numbers. If you can relate the mean value of this quantity for n plus m, n and m in a subadditive manner, then you get by the subadditive theory, you will get convergence. But this will not tell you what the limit value is, or even not a guess. This is very similar to the interpolation that was done by Franz, Leon, and Toninelli in 2003 for diluted spin glass model. That's where they got the idea for, the Bayati, Gamarnik, and Vitali. And Franz, Leon, and Toninelli are doing for sparse graphs what was done before by Guerra and Toninelli for the SK model a few years before that. And Guerra and Toninelli were after, was known in mathematical physics community that people could not even prove that the free energy of the SK model existed. This was quite annoying, so the subadditivity using this interpolation methods actually solve it. And towards the end of the lecture, part 4, I will explain to you also this interpolation method in principle, not for this problem, but for slightly different version of the same issue. So you will learn something that is commonly done in spin glass. Okay, so we are after now. I will go to the proof of go over the essential of the proof of the result that I mentioned towards the end of the first lecture, and I will repeat this result. So this is a joint work with Montanari. It's posted on the archive and it's going to appear eventually in another probability. And we are after the n goes to infinity, then gamma goes to infinity. Behavior that is coefficient of this coefficient that I told you, C1, C2, I'm going to find the number. And the idea is we will connect it. This is an easing problem on a sparse graph, but somehow it will become a problem of spin classes over a complete graph. And for problem of spin class over complete graph, there is now, first of all, there is much more developed and nice theoretical physics, and there is now much more developed and nice mathematics due to Talleyrand, Lachenko, and Guerra, first Guerra and Talleyrand, and then following up also by Lachenko and other younger people. Okay, so here is a theorem, and this theorem appeared on the one of the few last slides of the first lecture. So we will prove that 1 over n, mean bisection, max cut, not only are these things converging, but we will determine their value in principle. That is, we have the trivial factor gamma over 4, and then we have a correction factor square root of gamma, forget the 4, and then there appear a particular interesting constant p star. P stands for Parisian. star stands for star. And then, of course, this is not the answer. If gamma is 7 or 6, it's not like that. There is more terms, which we don't know what they are, but we know that they are much smaller than the first terms were for gamma. So when gamma is very large, we got the first non-trivial leading term, and it came from the theory of statistical spin classes. So that's really the end of the story of finding the C1 and C2 and trying to converge, because now we know what they are, we know when they converge, and there is no need to do that. Now you can focus your attention on getting the whole formula, maybe. And then, of course, there are these terms which disappear in the limit n goes to infinity. Okay. So first of all, let me tell you what is P star. In short, P star is going to be the ground state energy of the SK model. So let me remind you what is the SK model. The SK model starts with disorder, right? We saw it in the last lecture, but I'm repeating it now, more detail. We start with disorder parameter. It's a matrix J, symmetric matrix of size n, and the values of the J in the diagonal do not matter, because we are going to look at a quadratic form J sigma transpose G. This is going to be our Hamiltonian, and the JII is simply going to multiply sigma I squared, and plus minus 1, when you square them, they've always 1. So it's just an extra random variable which don't matter to anyone. But the Jij for I less than j is symmetric, right? So we don't need to specify both sides, we just need to specify one side. Those guys, as I mentioned, the Sheraton-Patrick proposal, to take the complete graph, so you have all of them, and each one of them is Gaussian, and we will scale the variance in such a way that they will have the same effect as here. Right? Here, we do not scale the variance, but we have only linear number of edges. Here we have now a quadratic number of edges, so we put the variance 1 over n to each one of them, so the overall effect will be the same. So that is the Sheraton-Patrick model, and it becomes even nicer if you choose diagonal terms to have a specific variance with respect to the off-diagonal, because then the matrix J you get is a Gaussian orthogonal ensemble on which you can study forever. We will not need too much to study about it, but it's very nice properties of this Gaussian orthogonal. Okay, so what we are doing, we are looking at a problem like that, except that instead of the Hamiltonian of the Ising with the graph, now we have a Hamiltonian over the complete graph using, so I will write it, we have H SK, sigma, which is 1 over 2 sum sigma sum and we can calculate the free energy. And as I said before, as in the other examples, it's always concentrate, so we can take the expected value. This is a sequence of numbers. This sequence of numbers was proved to have a limit. That's exactly the point of the Guerra-Toninelli interpolation. And this limit we call P star. At this point, you might think that I'm really cheating you, because I could have taken the same stuff for the HG, now I took it for another guy, so what did I gain? I just tell you no. The constant, which I don't know what it is another constant which I don't know what it is. But the point is we actually do know what it is. First of all, we know that, as I said, the limit exists, consequence of Guerra-Toninelli 2002. Secondly, as I mentioned in the first lecture, there is a so-called Parisi's formula. There is a prediction of Parisi that can give us, from the non-rigorous method of statistical physics, can give us a formula. More or less, not a very short formula, but it's more or less a closed form formula. It's solution of some nonlinear PDE and then doing some optimization of the set of solutions. So it's not a very easy thing to do, but it can be written in a relatively concise way, so it looks elegant. And moreover, Talagant in 2006 actually verified the Parisi's formula mathematically, so the theorem that this variational problem expression is equal to this limit is a mathematical theorem. Now, there is also, and here, this is all mathematics, and now I go to slightly some speculation about what happened when you try to actually solve the problem of constraint satisfaction problem. This will be, partially we will talk about solving the problem in the second lecture after the lecture, but what people know from, again, this is now statistical physics prediction. Statistical physics prediction, the Parisi solution, if I remind you from, I didn't do it last time, but I mentioned a little at least, that the Sheridan-Kirkpatrick postulate a certain structure of solution. This was wrong. And then Parisi came with a sequence of corrections, which are called 1 RSB, 2 RSB, 3 RSB, and so on. And towards the end of the first lecture, I explained to you a little bit briefly what 1 RSB should be. But the most complicated of them is, of course, infinite RSB. That means you need to do this procedure of corrections infinitely many times. For the Sherrington-Kirkpatrick model, the prediction from statistical physics is that you should have an infinite RSB. Now, this means, infinite RSB usually means that the set of near ground state solutions, the set of solutions, if you want, or near optimum realizations, is going to be of a very complicated structure. The structure, I mentioned to you, the cluster structure, zero RSB, replica symmetry, like one block. Everybody is near each other. 1 RSB is like a tree. You have branches, and this corresponds to a cluster of nearby solutions, another cluster, another cluster. 2 RSB, 3 RSB, infinite RSB is an infinite tree, which means that the solution set shutter in a very complicated way. And therefore, algorithms that try to find near extremal cuts are going to be very difficult to construct, because it's not that you can get something and go locally to somebody nearby. That's not going to work. They are all over the place and they have a very complicated structure. And that explains why standard combinatorial methods were also unsuccessful in predicting P star, because the combinatorial methods, on the one hand, never did statistical physics. They do classical probability. On the other hand, try to come up with an algorithm, which is even worse to do. So it's not surprising people worked for almost 20 years and relatively did not have much to show for their effort. I mean, they had much to show for their effort. They worked very hard and did ingenious proofs and so on and so forth. As far as the result, they didn't get it. And the reason is that they looked at it with their own, if you want, lenses. So this is the statistical physics is providing you here the right lenses. Okay, so let me stop here. Right? So the break has been declared earlier, because I will not finish this proof in 5 minutes, not in 10 minutes, so I will start with the proof. We'll take a 5 minutes break, and then I'll go over the proof and go over the algorithmic stuff and the purified stuff. So we are now with the 2/3 of power 4 or 6.
Questions so far? I have actually 2 questions. One question is concerning your theorem. You have small order of gamma and square root. Do you know what is the second order?
You mean this?
Yeah, these, for instance.
We get gamma to the 1/6.
1/6.
1/6, but I'm not sure that that we are optimal.
How about n?
This is supposed to be. This is supposed to be square root of n. 1 over square root of n, and I think you can prove that it should be 1 over square root of n. This is really fluctuation, right? This is forget the gamma, just compare this to its expected value. The expected value goes. Expected value also may deviate from the limit. So I would guess it's 1 over square root. If it's not, I don't think it is. You have a lot of randomness in the graph here, so I don't think it's like I don't think it's like this maximization problem which are extremely tight. But I might be wrong. We didn't try. The answer is we really didn't try either one of them. And the reason we didn't try either one of them is, well, we were just very glad that we got the answers. But it's a good question to look.
Another question is that in this model, your graph is not weighted. You know, each point is cut is all one. If you consider weighted graph, I mean cut may cost depending on the weight of the, let's say, the conductance of the bond. Is there any result?
As I will mention in the second part, there is a general principle. And the general principle is that you can take problems on sparse graphs, and when the parameter gamma or degree or whatever it is becomes large, the leading term after the trivial, this term is trivial because it corresponds to deterministic optimization of some sort, and the next term, next non-trivial term, will involve something that can be found by solving a Gaussian problem. Now, if your weights are sufficiently regular and not changing with this parameter gamma, whatever the parameter gamma means, that I can apply this, then, and this is done by in a paper only by Sen. So you see there was 3 autos, then there was 2 autos, then there was 1 auto. Okay, now there is no. So Sen is looking for other people now. Okay, so in his paper alone, he observed that what we did is not limited to cuts, but can be done on many models. Now, when you apply it on many other models, usually you will not be as lucky as ending up with a Sherrington-Kirkpatrick that Callaghan already solved for you. So you will move to a model with Gaussian, often very much easier, but for which you will need to do it yourself. So part of his paper is to say that certain problems are already done, and he mentioned which they are, and certain other problems are not done, but people who are specialized in spin glass models should do them now. Because before they looked very strange to them, now they are not strange because they come from a place where they are natural. So they are working on this, but not necessarily on the problem that Takashi mentioned, but one can try. But if the weights are all over the place, then it's a different story because they can mask the whole large gamma effect. We will see it when I go to the second part. Okay, so as I repeat, we want to prove this theorem, and the theorem has actually, it's a 6 theorem, right? There are 2 graph ensembles and 3 different graphs. Theorem says that you really get the same constant for all of them, and up to the sign here. And what I will do, I will prove less than 1/6 of the theorem. I will prove the case of the Erdo-Shreni case for the minimum bisection. I will focus on this. Everything else will follow later. Okay? So and I will also do only the strategy of it. Okay, so we start here. So we are going to look at the proof of the mean bisection only. The proof goes as follows. You first prove it for mean bisection and max bisection for the Erdo-Shreni case, because the independence here is more useful than the regularity. And the proof involves 3 steps. It involves concentration, interpolation, and a smooth max. And I will explain to you these 2. The concentration is essentially the same as this Bolov has shown. Azuma Hofting or classical concentration inequality, not exciting in this case. The second part of the proof is to extend it to the regular case. What you need to do that, you need to couple a regular graph with the Erdo-Shreni graph in such a way that the number of edges in the error between them is small. The problem is a little bit tricky because usually what you know is that this guy has degree exactly gamma every place. This guy has degree which is on the average gamma, but it's Poisson. So it has fluctuation of square root of gamma. So actually the number of edges in the difference between them will typically be of the order or even much larger than the quantity you're trying to extract. So you cannot simply say, oh, the graphs are small enough that I don't care about the difference. You have to do the coupling in a tricky way by arguing that the amount of edges that you are missing are somehow a constant. And it's the same constant that you change from here to there. It cancels out, And what matters is not the factor n square root of the gamma, but the square root of this square root. So now it's gamma to the 1/4, and therefore you will have a smaller error. Now, by the way, it is not true, we're not expected to be true, that the answer for regular graph and for Erdős-Rényi graph is the same for all gamma. It's only the leading term which is the same because they are somehow both going to the complete graph. But if you take gamma which is 7, there is difference. At least physicists predict different answers. Because then becomes important what is your tree limit that you mentioned in the first lecture, and will come, the tree limit will come not in this context which is difficult, but in the context of easing models in the next lecture, next week. Okay, so suppose we did that. The last step is to prove that the max cut, the unconstrained optimization, and the constrained optimization, the difference is smaller than the term that we want to do. And kind of it's clear because the leading term involves the size of a typical cut, and the size of typical cut involves the size of S times the size of the complement of S. So if you choose S and the complement of S not to be half n and half n, but some other fraction of n, then you take advantage of the fact that alpha times 1 minus alpha is maximum when alpha is 1/2. But the tricky part is to rule out the things which are almost n over 2, but slightly deviating from that. This you cannot rule out by using trivial arguments, so again you need to work a little bit harder. So there are technically tricky parts which, in order to move to the max cut and in order to move to the regular graph, which maybe mathematically were maybe the most challenging, but intellectually are probably the least interesting, because they involve people, you know, lifting weights and demonstrating that they are good at doing these things, but I don't know if there is really a big message here. So instead I will focus on the mean bisection, as I mentioned, concentration, interpolation, and smooth max. So first I will explain to you these 3 steps. Okay? So recall what we want to prove. Here is the mean bisection problem, rewritten in terms of the easing, ground state. We want to get this number here in front, so we need to take this quantity, divide by n, take the expected value. Now, here is concentration. Concentration statement, the variable is very close to its expected value when you divide by n. And we already know that from concentration inequality, classical concentration inequality. So we want to prove that this quantity is P star plus things which are small in gamma and small in n. That's our goal. Now we already know that the ground state of the SK is P star with log plus with log of n. So if we can prove that the difference between these two when n goes to infinity and then gamma goes to infinity becomes 0, then we are done because we simply take this constant here. And to Takashi's question about all the errors here, well, they will be involving in checking how much error you made here. And also, if you want variables, you need to look at the concentration error, but you can just look at the means right now. So the difference is, okay, so the idea is, in this business, the idea is an interpolation. Interpolation or smart path or Lindenberg method. We want to move from this situation to that situation in a kind of smooth and gradual manner. That's the idea. We want maybe either replacing the variables one at a time, from our graph edges to the Gaussian value. We are going to replace from the indicator on the graph to the Gaussian, or maybe we make some kind of a linear interpolation involving some parameter and differentiate along it. So I will show you actually both of them. I will show you the smart path, which is the method that people have been using in spin class, where you actually construct a continuous path and differentiate. And that's also in principle the Guerra-Toninelli-Talagram interpolation arguments, which are used in spin classes. And then later I will talk about this paper of Sen on the blackboard, and I will show you a much more general, and in this case much more powerful Lindenberg method, because it's less sensitive to details and achieve exactly the same result. So our paper, we were too smart for our own benefit. We realized that we can do something so elegant and complicated and very special. And then Sumawata came and said, you know, you can do it with more mundane method, and then you can do hundreds of other problems because you don't care about the detail. And I will give you also this kind of argument. Okay, so what is the idea of the smart path? So first of all, remember what we need, we are starting with this Hamiltonian, and also with the problem, we are also looking at Z and beta, which is a, or we are actually looking at this object. We are actually looking at this object here. We are looking at object of this type, the log, the 1 over n expected log of the sum of a certain Hamiltonian, where the variables here have quadratic form, and the variables here are going to be edges of a graph. If it's a Erdos-Schreini, it's going to be some Bernoulli variable. And we want to replace it with a problem where the variables have changed to Gaussian. And now on the whole graph. Okay, so we take this guy, and we want to go to that guy. So how do you do a smart path configuration? You say, well, let me take a mixture of the two, correctly interpolated. So at one end, when t is equal to 0, I will get the value of the path. So when t is equal to 0, I have here 0. So nothing comes from here. And I have here the graph g and gamma over n. And when t is equal to 1, I want to kill this, make it 0, and put here a 1. So I will recover the SK Hamiltonian. I also need to do one more step. At the end, I will get, this way I will recover the max energy for the SK, but also on balance configuration, because I never change the configuration. But I can maybe prove separately by the theory of SK that the maximum over balance configuration is almost the same as the maximum over configuration. You should remember that most of the configurations on the hypercube are balanced. It's a statement, you know, most of the, up to 1 over square root of n, most of the vectors are balanced. Okay, so I will not do step 2, but I will go over the argument of step 1, which is written here in red, to make sure that I will do it. And one more thing that you need to be careful is how do you shrink, you know, you don't know how do you shrink Bernoulli. You know, Bernoulli, these are 0, 1. You cannot make it a tiny number. But what you can do, you can play with your graph. My graph was random, so what I can do, I can change the probabilities. And I can play with my probabilities so that I start with gamma over n, and I end up with 0 over n, by taking gamma multiplied by 1 minus t. And this has the same effect as multiplying by square root of t, and the idea is that you do it in such a way that if you calculate the expected value of h of t squared, you get the same quantity and it doesn't change with t. That's the usual Stein interpolation in spin glasses. Mean is 0 in all of these things, or small, so you want to make sure that the second moment stays constant as you interpolate. Otherwise, it will give you another contribution. And the observation is that this is simply what we have here is just an example of a multigraph of IID. Okay, or if you want, we can change this problem to a problem with slight deviation. Instead of having single vertices, we now take a configuration model, so we allow the graph GT to be a multigraph, so we allow for multiple edges. It's small error, most of them are not going to be like that. With a Poisson gamma 1 minus t over n degrees of the edges. So this will be nice because now we can differentiate, everything here will depend on the parameters of this Poisson and the parameters of the Gaussian, and we know how to differentiate Gaussian laws and Poisson laws with respect to their parameters. That's also what Alagrand and Franz Leon and Toninelli have been using. They take Gaussian or Poisson models, and the distributions have very nice formulas, and you can differentiate all sorts of densities. And then all things are much simpler to do. So that's exactly what we are doing. Now, before we do that, let's see what we need to calculate. What we need to calculate is the expected value of the maximum, but the maximum is not a very nice formula. I mean, I don't know how to maximize, to differentiate with respect to t, the maximum function. Maximum function is not a differentiable function. So this is a smooth max. What we do what I told you before, that the ground state is really the limit as beta goes to infinity of the partition function, this quantity. So now I'm going to calculate this quantity, where was it? This quantity, okay, it's on your board, on the slide. I'm calculating this quantity, which is going to be a nice function. There is an integral, there is a sum over sigma, fine, there is an integral over the distribution of everything here, and I will appear at t, I can differentiate in t, for example. So what I know also is that if I take 1 over beta times this phi, if I divide by beta, and I subtract from the maximum, what I will get is a constant divided by beta. The reason being, you look at this sum, it's at least e to the maximum, and then when you take e to the maximum and you take the log will cancel the e, so you get exactly the e to the maximum. So this quantity is certainly bigger than that quantity, and at most it can be e to the maximum times 2 to the n. 2 to the n is a large number, but log of 2 to the n is only n, divided by n is only log 2, and at the end you also divide by beta, that's good news, so if beta will go to infinity, this will disappear. So if I take beta to infinity, I can get rid of this. But in order to get rid of this, I need to take beta to infinity before I take n to infinity. So I need a uniform in beta up bounds on the difference. Sorry, on the difference between this function at t equals 0, which is the one I want, and at t equals 1, which is the one that is supposed to give me the p star of quantity. So how do I control the difference between phi n, beta, gamma, and 0 and 1? Well, I can also write always a function at 1 as an integral of the function 0 plus the integral of the derivative from 0 to 1. From 0 to 1, there is only a linear line. So if I control the derivative in sup norm, I'm in great shape. So I will control the derivative in sup norm of this quantity. Therefore, and I will do it uniformly in n and d. Therefore, I will get a control uniform in n of this value between 0 and 1. Because of this bound, when beta is large, I will get a control over this between 0 and 1, and that's what I wanted to do. This is really repeating what was done also for sharing the pattern model. Exactly this principle. You want to control, you want to find something with 0, which is what you want. You invent another one that you can calculate. Try to interpolate in such a way you have control of the derivative. Now, of course, all the action is here, right? Everybody can write this program, but somebody needs to implement the program. And some problems are easy, some problems are hard. Also in Spindler, some problems are open, because you cannot implement this program. Here we will be lucky and we will be able to implement the program. Okay, so here is a lemma. We are going to prove that this derivative is bounded by some function which involve only beta and gamma. The function has, so n and t will not matter, so you see we have a uniform bound, c is some universal constant, 100. You can see our arrows also from here. And you can see that in principle, 1 over beta times this quantity will still grow with beta but decay with gamma, so we can just choose beta going to infinity very slowly with respect to gamma, so the whole thing will go to 0. We can always do that, but we will get certain error there. Okay, so the goal is to prove the lemma, and I will give you 2 proofs. The first proof will be taken from this paper, and it will be using this kind of interpolation technique, which relies on having very nice distributions. It relies on us choosing this Poisson for the graph, and the Gaussian for the escape model. But the other method, which will be a Lindenberg method, will be rely on much less, and therefore in this paper of Sen that I mentioned, which is written here, the archive version, he can essentially tells you how to transform your favorite problem and move it to a problem on a complete graph if the degrees are large, and you get some problem on a complete graph with Gaussian disorder, which you may or may not be able to do, but it's believed that those problems are always simpler than the problem you started. So you must have improved a little. And if it happens to be that somebody else already solved the other problem, you certainly improve them. Okay, but we are not doing that. We are taking this particular example with a quadratic, and so on. And let me introduce some notations. In these problems, there are always everything is controlled by multi-replica overlaps. And multi-replica overlaps, what you're doing, what is an overlap? An overlap is the following. You take two vector sigma from our balance configuration. These are vectors, sigma 1 and sigma 2. They are all vectors. They belong to this set. They belong to this set. Sigma 1 and sigma 2. They exist here. Oh, sigma 1, sigma 2, sigma c. They are chosen independently, but they are chosen independently from our measure mu n t beta j. What is mu n t beta j? it's essentially the same as this guy, mu n, except it's now much more complicated. Mu and beta j, sigma will involve 1 over z and whatever, some constant. And then in the exponential, you will have the Hamiltonian sigma beta plus the Hamiltonian scale of sigma, which depends on j, times the square root of t, something like this. So this is really, coming back to slides, I'm looking at this, putting this Hamiltonian in my exponent, whatever it is, and then rewriting the measure, and I'm taking configuration from this measure in a particular point t in the middle of my smooth path. I am differentiating t in a particular t, so I'm taking these particular things, and here it is. There is no, okay, I did not write the beta for some mysterious reason. I should have a beta here too. Or maybe there is a beta here, it's supposed to be the argument of this. But anyway, this is a constant that depends on n, t, j, and beta, and this is the weight which came from there. Okay, so what is the multi-replica overlap? Let's suppose L equal to 2. If L equal to 2, what we are doing is taking sigma I of 1 times sigma I of j, and summing up. So it's simply an inner product. An overlap. An overlap is an inner product between two vectors of the hypercube. What's a multi-replica? You just lay down 7 vectors, and you do an inner product, all of them in one coordinate, and you sum over all the coordinates. This is called the multi-replica. Notice the following. First, Q1 is 0. Why? Because if you have only one vector, you are just summing it up. When you sum it up, you get 0 because you are looking at balance configuration. What happened to all the other overlaps, all the other multi-overlaps? They are all bounded by 1. Why they are all bounded by 1? Well, this is the product of plus minus 1, at most 1. You sum and divide by n, certainly bounded by 1. That's all I do. So I have all of them are 1, and the first one is 0. Let me also call kappa beta over square root of gamma. That's fine. You see, these are the terms that appear here more or less. Okay, so if I differentiate, I will get two terms, right? I differentiate, I have this complicated Hamiltonian, I differentiate with t. This is really supposed to be 1 minus t. I differentiate in t, I will get something that counter differentiate in this guy, and I called it 1, and something that counter differentiate in this guy, actually this guy is 1 of it, and I call it 2. The difference is in 1, we will have some derivatives involving Poisson, or Gaussian, and in the other one, in 2, we'll have some derivative involving SK. And when we do this derivative, then it's a kind of an calculation I'm not going to subject you to, but you have an energetic PhD student, then you have good calculations. and if you do this calculation, you get a nice explicit formulas which are written in terms of this parameter kappa that is supposed to be small, and all sorts of multi-overlaps. Okay, we can do this job. We did it, it's written in the paper, we get it. Okay, so now, if you look at this scene, you will see the following. First of all, the term 1, you don't worry about because this will be 0. So this sum starts at 2. And okay, this term starts at 2. And the point is that if your kappa is very small, so you can expand log cosine hyperbolic of kappa and tangent hyperbolic of kappa to a power series if you want kappa. And you will look what happened to the leading terms. So the leading term will give you exactly, the leading term will appear only when this n is equal to 2, and it will exactly cancel this guy. And everybody else will be small. write it. And when you do this calculation, you are done. So there is a dot, 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 dot. But anyway, I'm going to now explain to you a superior method. So superior method. So superior method is in this paper of Subabrata-Sen, and it's the following principle. First of all, it's not easing related. You can take your favorite model, it doesn't need to be cut. Take any function, take any of the problems I mentioned to you, any problem that moves to a statistical physics problem, which is sitting on a sparse graph, and there is some parameter of degree that you can take to infinity, you can move it to a corresponding problem with Gaussian variables. What is key is to use the Erdős-Rényi, the independence, and to use the gamma very large. The idea is to replace this smart path, to replace this very careful interpolation in T, which was very important in the theory of spin glasses, and also very important for us when we do this whole fancy calculation, with a Lindenberg method which is good enough for it. Here are a few examples that you can do with it. You can take, instead of cut to 2, you can cut to Q's groups. Right? We cut the set to 2 pieces, you can try to cut it to 3, 4, 5, and ask about the maximum that you can do, mean, max, bisection, whatever, for such a cut. Since a cut has Q parts, you are not longer going to end up with easy spin. Now you need for every vertex to decide whether it's in 1, 2, 3, or Q. This will give rise automatically to pot spin glasses, and pot spin glasses have been done by Panchenko recently. So you can just take Panchenko's theorem together with what Subabrata was doing, he did it in his paper, and get answers to max Q cut for any integer Q that you want. You can also take a problem of max up for linear equations over 0, 1. Linear equation over 0, 1 are actually not a really difficult problem to solve. You can do Gaussian elimination. These are binary equations where you take modulo 2 and match with a given number. These are exactly the equation one happens to find often in communication theory. You code the message and you want to decode it by a linear decoder. That's exactly what you do. And these equations are really what is called error-correcting codes. These are codes that allow you to transmit over noisy channels while you make errors and recover them because of the redundancy in your code. So max up is a question of how many errors will you be able to deal with in a unique solution. Now, this is done by linear elimination when you can do it, but sometimes you go beyond the regime of linear interpolation. You are allowing actually errors, but you try to make as minimum errors as possible. Now the problem is not easy at all, because you are not looking for the solution to the problem modulo 2 over the finite field, which you can do using linear algebra, but you're actually looking at the minimum norm. The norm here is a number of ones in deviation from the solution, because there is no more 0. There is no more, you are not in the image. The vector that you specify is not in the image. You try to get as close to it. This is a well-known NP-hard problem. This is called the unsat phase. And if you assume that you have exactly k variables per equation, you look at this problem, this becomes exactly the problem of what is called k-spin. Because the modulo that you do in the linear equation transform into these sigmas into taking sigma 1 times sigma 2 times sigma 3 times sigma 4 and exactly k. This is called p-spin. And p-spin problems was also done by Taleb. So the p-spin model gives you the solution to this one. And you can do more problems. Panchenko recently did the KSA, and any energetic person can now write, I think, a paper on this business. Oh, okay. If you can do the Gaussian KSA, you can write. Okay. So before I go back to computation, can you raise, is it possible to raise the board? Let me just complete on this graph, I will complete for you the key argument from Subabrata's Sen proof. So we are trying to compare, remember, what our goal is to compare this Pn at 0 to the Pn at 1. This is a 1 over n expected log. These are our smooth max. And we don't want to differentiate. We want to compare the situation we have. In general, you have a general function. We can deal with general function. To make this notation simple, I will keep the quadratic form that we have in our example. So I will do is lemma 4.4, which is the key to the argument, how to move from what I did. It's easy to escape, but in general, from sparse model to a complete graph model with Gaussian in a general case. So I write my Hamiltonian. It's going to be the same Hamiltonian. The difference will be, in the case of the sparse graph, I will have, as a coefficients here, Bernoulli variables, right, corresponding to the evolutionary graph. Here are my Bernoulli gamma over n. This represents the indicator on having an edge, and the normalization 1 over square root of gamma that I told you I need to take in order to make sure that when I change the probability of the Bernoulli, I don't change the size. So this is what I want, this guy, and this is what Subabraka or I or everybody will believe is the same. You replace the A by normal. So replace the A by normal Jij. These are not exactly the normals we put here from the SK. What we are trying to do, we are going to replace the A's by normals, but we're going to make sure that we keep the mean and the second moment to be the same as the ones we found for the A. So we need to calculate what is kappa 1, should be the expected value of Aij. Because Bernoullis are no center, so we have to take care of that. And that's going to be a square root of gamma over n. Right? So it's like that. And kappa 2 plus kappa 1 squared. That's going to be the second moment. Right? That's the second moment. Squared. That I want to be the second moment of Aij squared. And that's because if you take this Bernoulli and take the square of it, you will get this. Okay, so from this, of course, you can calculate what is kappa 2. If you want, kappa 2 will come to 1 over n minus gamma 1. This is just algebra. Okay. So now, but you said, oh, really, but you cheated, right? You were not supposed to calculate, the guy with the J tilde, you were supposed to take the guy with the J, right? So let me calculate for you separately the relationship between them. So let me write the Hamiltonian sigma J tilde. That's 1 over half some sigma I sigma J in my example. This has to be done separately for each one. Now what I want to do, I want to write it like that. So what I'm doing, I'm writing for you a normal with a non-zero mean and a certain covariance in terms of a standard normal or a normal with zero mean, just simply by adding the mean and multiplying by the right quantity to move the variance from one to another. Right? So this is just writing one normal in terms of another. Okay, so I get kappa over 1, some sigma I square, plus square root 1 minus gamma over n, HSK sigma, which is a 1 with the Jij, minus 1 half. There was also a contribution from the diagonal, which was not present. Here I should have done that. Maybe I should have done it just that. SK actually have, and in our sparse graph. Now notice the following. First of all, this goes to 1. It's not going to cause much trouble. Secondly, this guy is only normal 0, 1 over 8. In any case, it's of constant order, and everybody else here is of order 8. So this is tiny and doesn't cause any problem. Now, you can be actually very worried about this quantity. Because this quantity should grow like n squared. It can dominate everything here. But notice, luckily for us, and that's the reason we took sigma in over there. Now you discover what was the role of the balance configuration. The role of the balance configuration was to eliminate the linear factor, the mean factor. And it's true that this is important because we know that the mean bisection corresponds to ferromagnetic easing. Ferromagnetic easing has nothing to do with the disorder model because it's maximized by all pluses or all minuses. But the balance configuration preventing you seriously from doing that. So you actually lose this thing, and you can see that now this guy is effectively the same as this guy. So if you can move from A to J tilde, you can later move to J. So Subrabata put it in this framework. Now that you put it in this framework, you can use the result of the Chatterjee. So there's a very nice paper of Chatterjee in 2005 that you will find in the archive. Chatterjee is one of these mathematicians. There are a few of those, some of whose best papers are never published. So this is one of them. So people cite it happily, but it's only appearing on the archive. So probably 11 years by now, we probably never will publish it. Anyway, what's in this paper? In this paper, he's doing a particular, very nice application of the Lindenberg method, and he says the following: take a function A from Rn to R, which is 3 times continuously differentiable, and take two different vectors, x, which is x1 up to xn, and z, which is z1 up to zn, and they are both independent. All the coordinates of x are independent, and all the coordinates of z are independent. Well, they don't talk to each other. This is just a vector of independent coordinates, product measure, product of x's, and product measure for the z's. And we also make sure that the expectation of zi is the expectation of xi, and the expectation of zi squared is the expectation of xi squared for I equals 1. The variables don't need to be identically distributed, they just need to be independent and share the same first and second moment. This is our situation here, right? You see, these are our Aij compared to our J tilde ij. That's why I wanted to make sure that the mean first two moments are the same. And now we want to bound the expected value of f of x minus the expected value of f. This is a self-derivative in xi in one coordinate of our function f. It's a big, complicated function of many variables. And then we take the sup over all argument x and the maximum over all r. This is one contribution. And the S3 is a contribution that carries out the effect of the third moment. The third moment is the first place where the z's are not the same as the x. And the S3 is a constant 1/6 that nobody cares. There's a sum from I equal 1 to n expected value of xi2 plus So if you think about this, is exactly the Lindenberg method, except that the Lindenberg method is done by Lindenberg for the sum, or a function of the sum. And Chatterjee observed that what is important, the function be smooth and have nicer derivative. And the sum has nothing to do with it. So this is very useful for us because we are going to employ it to this function here, f. What is our f? So this is Chatterjee's result. employ it. This is the subatract side operation. We are going to employ it for f of m, which is the expectation g of m. And this is g. This is g. So what we are after comparing expectation of g of a minus expectation of g of j and checking that it's small, right? That's comparing our two functions of input. So we want to bound the difference between these two, which is the same as replacing in m the aij by the jij, but not the j, but the tilde j. So this is exactly the framework that we need. So here is in sense paper, and big N is going to be n choose 2, because our basic variables are living on the edges. So we have the XE is LE, and the ZE is the J tilde E. And if we do that, then exactly this quantity is what is the E doing here? I'm wondering why I have an extra E. I think I don't have an E. Oh, this is just G. This is a type. F is G. And G is this. G is this. Okay, here is the one over n, right? Okay, so what I need to do, I need to check now the error, the S3 and the bound of the derivative. So let's calculate the expectation of an x cube and the expectation of a z cube. Well, the expectation of an x cube, the x is an a, the a is Bernoulli, divided by that, you get 1 over the square root of gamma to the 3, and you have the gamma over n once, right? Because either it's 1 or it's 0, you don't get more than that. So this is going to be 1 over gamma to the 3 over 2, and gamma over n, or 1 over n square root of gamma. And what is the expectation of a normal? Well, our normal has variance 1 over n. It has variance 1 over n. So its moment will be C 1 over n to the 0. And you might be worried about the mean, but the mean is of order 1 over n, so its effect on the third term is nothing. 1 over n is even smaller than that. The conclusion of these two things is the fact that S3 is less equal to a constant times n divided by square root of gamma times n. This term is going to be the bigger of the two, and you will multiply it by n. N is n choose 2, so you will get out of that Cn over square root of gamma. That's a contribution of S. This is growing with n, but hopefully this quantity will kill it. Okay, so in order to calculate this one, you need to know something which was also used in the calculation of the smart path. Whenever you define differentiate, this is really your normalizing constant. Whenever you differentiate the log of the normalizing constant, what you end up with is the same as calculating the piece in the differentiating of the derivative according to the Gibbs measure, according to this measure. That's one of the nice things about differentiating Gibbs measure. So in particular, the derivative with respect to E of G is going to be beta over n times the average of F. Here F of E is sigma I, sigma j, when E is ij. So you want to differentiate, for example, with respect to one of these A's, or one of these N's, you will get this expectation in the bottom multiplied by the whole Gibbs measure, but then you have the factor beta from here, and you have the factor 1 over n from here. So that's what happened to the first derivative. And in the same manner, the second derivative will give you variance calculation. It will give you c beta squared over n times the second moment minus the first moment squared. And if you calculate the third derivative, which is what we are after, you will get something which will behave like beta cubed over n times the constant times the size of the third derivative. Now remember, this function is bounded. So obviously what you got here is just a constant beta cubed over n. This constant is going to multiply this constant, eliminate the n, and we will get the beta cube over square root of gamma, which is exactly what I claimed we will get with the smart. And this will work for a general nonlinear function, sigma of the variables, and for a much more complicated structures of graphs, hypergraphs, and all sorts of things, or like Takashi suggested, weights, and all sorts of things. It's not so sensitive as the first approach. It's really using the Lindenberg approach of changing from one variable to another. As long as they are independent and you match the first two moments, you will be doing good shape if your function is differentiable 3 times. Okay, let me do very briefly, in 10 minutes, go over part 5 of the lecture. Can you count this? And we will skip part 6 completely. I will do part 6 in a future lecture. I just want to mention that this scope of Chatterjee, or this argument, this idea, is also key to what we will do for graph homogenization in lecture 4. So lecture 4 will really be developing this principle of approximating smooth functions, but in a much more complicated setting than the one mentioned here. Okay, so let me repeat what the goal now is. We found that the value of the mean bisection can be determined for Erdos-Renyi graphs and is more or less constant over all Erdos-Renyi graphs. But what about the algorithmic problem of finding the mean bisection itself, not the value? Maybe I write incorrectly. I don't want to find the mean bisection. I want to find the bisection that achieves the mean bisection. This is still a very difficult problem. That's the problem of finding the ground states in our Hamiltonian. We did not really solve it. We found the value, but never found the actual minimizer. Parisi also doesn't find the actual minimizer. Okay, so we want to find the mean bisection for a specific graph. Also finding the value for a specific graph, not up to the leading term, but the actual values, the actual numbers, that correspond to finding the maximum of this quadratic form subject to this constraint. Right? So here is an example of a drawing of a random matrix with one AIG is one FI. You see that this is a very complicated thing to do, and this is an integer quadratic form, but over integer variables. Quadratic form over many integer variables, very difficult to do. Okay. What you can try to do is to do some kind of Lagrangian regularization. You want to move to a place where the problem is easier to do. So first step, you don't really want my constraint. Here is a way to put the constraint in. You just subtract a big lambda times the sum square, right? So if the sum square is not zero, this lambda very big will make this going to zero, and therefore force this new problem, which is unconstrained, will really be solved by the constraint problem. In principle, you should put here lambda equal infinity, but if you have this graph, this A come from this graph, you can check that taking lambda, which is gamma over n, is already producing here a sufficient pull backward to make sure that this guy will come to be very close to zero. So I'm not going to go over this. So now, this choice is exactly the same as subtracting from A its expected value. That's why I wanted this choice. It's exactly the expected value to A. So I have the problem opt G, and opt G is the maximum of this quadratic form. Now, variables lost the mean, but still integer constraints. Okay? What we know with high probability that typically the graph would look like that. Right? This is what we calculate. 2n p star square root of gamma, blah, blah, blah. So the leading term is going to be this number p star can be found by numerical simulation, and it's some number 1.5264 times n square root of g. This is a solution of this, at least for most graphs, and for large n. Okay. Now we can think of spectral relaxation. What is spectral relaxation doing? So look, instead of working on the hypercube, why don't we work on the hypersphere? That would be much nicer. Now our variables are real. So what we can do, we can replace this plus minus 1 by the hypersphere of the right size, and what paper of Krivelevich, Sudakov together, and then a paper with Wu at 2005 proved that, okay, if you solve this problem, of course, on the hypersphere, this is just an eigenvalue problem, right? This is the problem, the matrix is given, you're maximizing a quadratic form subject to the norm of the vector. You just look at the maximal eigenvalue. So you get n times the maximal eigenvalue of the matrix minus its expected value, and they analyze this particular Bernoulli shifted matrices coming from the GOE, and they prove that the lambda max of these things is actually going to grow to infinity. Right? So instead of getting square root of gamma times a constant, when gamma is order of 1, or you get a big thing. Right? So the factor is huge. It's not even, there is no relation between what you did and what you should have done. Okay, so this is really poorly, doing it very poorly. And here is an illustration what happened when gamma is very large, the eigenvalues look like that. And when gamma is getting very small, you're no longer looking like the semicircle. You have these peaks, but you also have outliers here, and they start growing, and they disappear when you becomes large. They already got, you can see them already trying to get out of this picture. Of course, I could have made this picture smaller, and you will really see them disappearing. In general, you should believe me or believe television group that this is true. Okay, so what we are going to do instead, we are going to replace this optimizing problem by a semi-definite program. What do you do in a semi-definite program? What you do, you write, this problem can be alternatively written, so writing sigma here and sigma transpose there, you could move the sigma transpose to this side. This is just a vector, matrix, vector, linear algebra can be written as a matrix times vector, vector transpose. And then look at the trace, which is what it's doing here. Okay, now you observe that all your variables are sitting in this matrix X, and what the matrix X should satisfy is that its diagonal terms are all 1, right? Diagonal terms are all 1 because they're exactly sigma I squared. Secondly, it should be a positive semi-definite matrix because sigma transpose is a positive semi-definite matrix. And thirdly, a lot of more other things. Now I forget the thirdly, and I keep only having diagonal 1 and positive semi-definite matrix X. And I solve this problem now on the real. So now I can still do this very nicely. This is the SDP method that I mentioned before. So I can do semi-definite programming. And this paper of Montanari and said, prove, using, in some sense, techniques close to the techniques we've been doing, that on the Erdos-Renyi graph, with gamma which is order of 1, with high probability, the solution to this problem is 2 times square root of g of gamma plus small order of square root of So you did not get the optimal error, P star, but you got a factor of 2 instead of 1.5. So you got a factor of 4/3, but this is very easy to calculate. As easy to calculate as a spectral relaxation, almost as easy, but much better. So this shows you that the SDP behaves much better than the principal eigenvalue and is more suitable for relaxation in this instance. So you saw that the choice of the regularization here came from subtracting the mean, and the idea of doing that is all coming from intuition. It's not directly statistical physics, intuition that you learn from statistical physics that you employ in your design of algorithms. Okay, let me go very quickly over the proof outline in the case. There's a proof outline in the paper of Montanari and Sen. What you do, you're going to interpolate in rank. Right? So you try to compare, we already learned interpolation is a good idea. So this is kind of going to be a theme in this sequence of lectures. You have something you want to do, you have something you know how to do, you want to relate them. So what you do is just make some steps on the way. It's a classical approach of analysis to a problem. You want to go from here to here, you take many, many small steps. That's usually good. So here, the small steps will be n small steps related to the rank of the matrix X. So I'll define op k of G is a problem that we have at hand, except I added a constraint that the rank of the matrix X is less equal to X, to K, okay? So I put a rank constraint on the matrix X. Of course, if I take the problem N, then I put no constraint, because every matrix of size n by n has rank at most n. So the answer, opt n, is SDP. What happens if I put opt 1? If I put the rank 1, and the diagonal element are 1, you can check that there is only one possibility, that the matrix is sigma, sigma transpose. First of all, a rank 1 matrix always looks like sigma, sigma transpose, no negative definite. And if sigma squared is 1, well, there are two numbers, 1 and minus 1. So opt 1 is what we start with. So what we want is this one. And of course, as you increase the rank, you relax more. So you have a monotone sequence that connects from what you want to what you did. Now, equivalently, I can write opt k differently. Matrix of rank k, I can write positive definite matrix of rank k. I can write as a sum of it's a sum of matrices of size n by k. I can write it as a matrix n by k times its transpose. This will give me a matrix of size k. Now, the difference is the element sigma I here is what is so-called Eisenberg spin. It's a vector in Rk, k is fixed, whose norm is 1. So it's a vector on a sphere of dimension k. Now, a vector of a sphere of dimension 1 is only plus and minus 1. But start with dimension 2, you have the first one is a circle, then a more complicated, and so on. So opt k is now a problem of a spin model, but it's a spin model of the Eisenberg type, right? You can rearrange this expression as a maximum of the sum over ij. This is your coefficient. And then what replaces the sigma I, sigma j is the inner product between the vector sigma I and the vector sigma j. These are vectors of the unit sphere of dimension k. So you relate all the opt k problems are all problems of spin class type. Okay, so what do we want to do? We want to do the following. We want, first of all, to do what is called higher, or what they did. First is a higher rank Grothendieck inequality. And Grothendieck inequality is a relationship between opt k for fixed k and the SDP, which is opt n. So you want to show that opt k is, of course, smaller than opt n. That's not a problem, but you want to get a corresponding lower bound to say that if k is large enough, these opt k are going to be a good approximation to the SDP, because after all, you're after this guy, right? That's what you want to find. So if you have this lower bound, which is an extension of the method of Grothendieck, which is a very nice result by itself, this has nothing to do with spin classes. Then you have this inequality. Now you can compare the opt k between the A and the X, between the A and the J, exactly the same way that this Lindenberg approach. But now for a different problem. Why not? So if you can relate, now lastly you can analyze the SDP for Gaussian. Because if you have the GOE, I told you, GOE is great. You can can do lots of calculation involving even you can analyze the performance of an estimate. Okay, so the conclusion, let's summarize what we saw here. We saw extremal cutting random graphs become balanced easing spins sigma I plus minus 1. SDP is related to vector spins on the sphere, sk minus 1. There is a universal connection to spin classes as gamma goes to infinity, which applies to cuts, to these vector spins, and to any other model, I will add. That's a paper of Sloboda. But before you get extremely excited about it, this does not tell us anything about what happened when gamma is fixed. It's all relay on taking gamma large. Because at the end of the day, we had essentially like a CLT business, right? We had this enormous slope of gamma, and then became a normal. Or if you want a Lindenberg method, at some point we did something similar to CLT, or to approximation. In particular, I repeat, go again to the problem of Zebova and Bocher. We want to prove that if the graph is regular, fixed gamma greater or equal to 3, with high probability, max bisection plus min bisection is the number of edges plus little order of n. Now you can see the motivation for this one. If the problem was indeed Gaussian, this would be trivial, because this is just a minimum of a quadratic function of Gaussian. This is maximum of a quadratic function of Gaussian. Quadratic function, but with a Gaussian in the matrix. Gaussian has the law symmetric, so you will conclude this variable is in law the minus of this variable. And there is not even an error here, nothing. It could just be equal. Problem is our variables are not to Gaussian. Now we matched our variables to Gaussian, but we matched our variable to Gaussian only when gamma is large. If gamma is not large, Bernoullis are not Gaussian. They are 0 and 1. There is nothing you can do about it. You cannot make them negative. So the problem is still open to anybody who is energetic enough to do it, or no, not energetic, has a good idea how to do it. So this is not a question of energy, but a question of cleverness. And in addition, one can look at various versions of the general program that says, you know, you take a problem, it becomes a Gaussian problem, but you can take a problem that you care, make it the Gaussian problem that you still care, solve the last one, go back like what I did here. I actually did the whole part. I just didn't just connect them, but I did all the work around. So you can do all the work around. And the Gaussian models might themselves be challenging. And so this is the connection. So to summarize, we see the whole program of extremal cuts. We also saw the connection to algorithms. I will not go over algorithmic aspects in the other lecture. There are many algorithmic aspects that have been done by other people, because actually the whole point of using statistical physics was also to help in finding algorithms, not just for probabilities to have fun to calculating formulas, but I will stick in the remaining 3 lectures to